Welcome to this explainer. Today, we're decoding the hidden feedback loops that actually control our Earth systems. If you're currently prepping for your A-level geography exams, you already know that Earth Life Support Systems, or ELSS, can get a little overwhelming. But honestly, by visually mapping out these interconnected water and carbon cycles, we're going to make these complex mechanisms crystal clear and, most importantly, totally unforgettable. Let's dive right in.
Okay, so here's our roadmap for today. We'll start with systems and dynamic equilibrium. Then, positive versus negative feedback. From there, water cycle feedback loops, followed by carbon cycle feedback loops. And finally, we'll wrap up with tipping points and thresholds.
All right, Section 1, Systems and Dynamic Equilibrium.
To really understand when a climate system goes wrong, we first have to understand what it looks like when it's functioning right. And that brings us to dynamic equilibrium. Basically, this is a state of balance in a system where inputs and outputs are equal. So the really crucial point to remember here is that dynamic equilibrium isn't just completely static or frozen. It's actually a naturally fluctuating baseline. Think of it kind of like gentle swaying tundra grass, bathed in a warm sunset, right? It moves back and forth with the wind, but it stays firmly rooted in place. You'll see small variations day to day, or even year to year, but overall, there's no net change.
You can see this visualized really well when you look at a steady-state baseline. It represents no long-term change in the system's store or flow. The current state of the system kind of undulates around it like a wave. It naturally increases and decreases over time, sure, but it always returns to that central axis. It's just a beautiful, self-regulating balance.
Moving on to Section 2, positive versus negative feedback. This brings us to the two main actors in our climate systems. Now, a quick heads up for geography, positive absolutely does not mean good, and negative does not mean bad. Positive feedback amplifies an initial change. It creates this massive snowball effect, pushing the system further and further away from its normal state. Negative feedback, on the flip side, lessens the effect of that original change. It acts as a self-correcting stabilizer that actively works to reverse the disturbance and push that fluctuating wave back to its safe baseline.
If you ever struggle to visualize positive feedback in an exam, just think of this classic analogy, the microphone. Imagine placing a microphone way too close to a speaker. It picks up a tiny, faint sound, which then plays louder out of the speaker. The microphone then picks up that newly louder sound, plays it back even louder, and the cycle just repeats instantly until you get that awful, screeching noise that totally hurts your ears. It is a completely self-propelling chain reaction. I want you to keep that screeching speaker in mind as we look at global warming.
Section 3, Water Cycle Feedback Loops. So the contrast here is pretty stark. Bright, white snow and ice represents the albedo effect. Albedo literally just means whiteness or reflectivity. Ice reflects about 85 to 95% of incoming solar radiation right back out into space. But on the other hand, you have the dark, deep blue ocean. Without that protective snow or ice, that dark surface absorbs a truly massive amount of the sun's heat.
And because of that contrast, we get a frankly terrifying positive feedback loop. Let's walk through the causal chain together. Step 1. Initial global warming melts the sea ice. Step 2. This exposes the darker ocean water below, which means a lowered albedo. Step 3. Because the surface is now darker, way more sunlight is absorbed rather than being reflected. Step 4. This extra absorbed heat warms the ocean and the atmosphere even more. And Step 5. Well, that extra heat melts even more ice. It's the microphone getting closer to the speaker. Warming causes melting, which literally causes more warming. But hey, it is not all doom and gloom here. We do have negative feedbacks acting as the heroes of our story. Take the cloud cover loop, for instance. As global temperatures warm, we actually get more evaporation from our oceans. That leads to more condensation and a big increase in low cloud cover. And those fluffy white clouds, they have a really high albedo, so they reflect sunlight away from the Earth and actually cool the surface down. It's just a perfect example of a negative feedback mechanism stepping up to save the day and restore dynamic equilibrium.
Okay, Section 4, carbon cycle feedback loops. Let's talk about what I like to call the detritus deep freeze. Beneath those incredibly beautiful cold landscapes of the Arctic lies the permafrost. That's ground that remains totally frozen for at least 2 consecutive years. This permafrost acts like a giant natural freezer for ancient dead plants and animals that never had the chance to fully decompose. It is a massive carbon sink. In fact, these soils contain a staggering accumulation of ancient organic matter, storing up to 1,850 billion tons of carbon, all safely locked away. Well, safely locked away until now anyway.
See, because the Arctic is currently warming at double the global rate, we are triggering the much-feared permafrost methane time bomb. Here is the positive feedback causal chain you absolutely need to memorize for your exams. Rising temperatures thaw out the permafrost. This exposes the ancient organic matter, essentially waking up dormant microbes. Now, because the ground there is often waterlogged and lacks oxygen, these microbes engage in anaerobic decomposition. As a byproduct of that, they release methane, or CH4. And methane is an incredibly potent greenhouse gas, way stronger than CO2 at trapping heat, which just amplifies the warming and melts even more permafrost.
And honestly, it's not just the permafrost we have to worry about here. We also need to look at ocean warming. As the atmosphere warms, the oceans inevitably warm up too. But here's the catch. Warmer oceans actually lose their ability to dissolve and absorb CO2. We call this the ocean mechanical pump slowing down. Because the ocean is absorbing less CO2, more of it just stays up in the atmosphere, trapping more heat and warming those oceans even further. It's just another incredibly powerful positive feedback loop.
Fortunately, just like we saw with the water cycle, the carbon cycle does have its own negative feedbacks. A really major one is carbon fertilization. Since plants use CO2 for photosynthesis, having all this extra CO2 in the atmosphere actually acts like a giant fertilizer. It stimulates plant growth. As vegetation grows faster and larger, it locks up more carbon right into its biomass, pulling it directly out of the air and helping to temporarily cool the Earth. It's nature's natural balancing act, trying its hardest to pull us back to that baseline.
And finally, Section 5, tipping points and thresholds.
This is where we encounter the concept of a tipping point. Basically, a tipping point is a critical threshold. Once you cross it, a change becomes entirely self-propelling and, worst of all, irreversible. The absolute best analogy for this is a glass of water sitting on a table. You can tip that glass slightly, and if you let go, it rocks right back to its upright, stable position. That's negative feedback maintaining your dynamic equilibrium. But if you tip it just 1 single degree past a certain critical angle, the glass falls, the water spills everywhere, and simply standing the empty glass back up won't put the water back inside. The system has permanently changed.
So, building on our earlier graph, we can now clearly see what ecological collapse looks like on a systems level. Imagine that fluctuating wave crossing a tipping point threshold, usually represented by a steep, dramatic cliff on a graph, and dropping down into a completely new, lower state. This is what we call metastable equilibrium. The environment has fundamentally and irreversibly shifted to a brand new baseline.
And guys, this isn't just theory. Leading scientists are deeply, deeply concerned about this. Professor Tim Lenton describes passing these thresholds like a series of falling dominoes. He notes, it's as if the slope steepens so much that we tumble headlong into the abyss. Triggering one single tipping point, like the melting of the Arctic sea ice, warms the planet just enough to trigger the next one, like the thawing of the permafrost. The momentum just completely takes over.
The stakes here are just incredibly high. The interconnected stresses between our water and carbon cycles are compounding every day. Recent computer models mapping out these feedback interactions suggest that catastrophic breakdowns in vital ecosystems could happen way sooner than we originally thought. As Professor Simon Wilcock quite starkly warned, due to these runaway feedback loops, we could realistically be the last generation to see the Amazon.
So, to wrap up our rigorous journey today, let's quickly review the core mechanics. Dynamic equilibrium is the natural balance maintained by negative feedbacks, like our cloud cover and carbon fertilization. However, runaway positive feedbacks, like the loss of the ice albedo and the detonation of that permafrost methane time bomb, threaten to push our interconnected water and carbon cycles past dangerous dipping points. And if that happens, our ecosystems won't just struggle for a bit, they will irrevocably shift into a completely new, metastable equilibrium.
I'm going to leave you with this final, provocative thought to take into your exam prep. Consider this your exit ticket for today's explainer. Of all the feedback loops we explored, which one do you personally believe holds the ultimate power to tip the scales forever in the Arctic? Is it the darkening of the oceans, or is it the thawing of the permafrost? Think about the evidence, justify your reasoning, and keep analyzing the world around you. Thanks for joining me on this explainer, and happy studying.